Okay, we'll go ahead and get started. Hopefully, you guys had a good holiday weekend. I did. I needed the extra time to relax a little bit, so hopefully, you guys got relaxed and caught up on some stuff. I want to get into today's lecture. Two things, though, before we get started. Number one, you want to think about getting the lab manual and the software. So I've already talked to a couple people by phone and by email, by text. Some people have already gotten the manual or at least sent for the manual. We got a couple weeks left, but you don't want to wait till the last minute. Everybody has to be able to hit the ground running on the week 6. We'll start the lab. So start thinking about that. What I will do is I'll put up, I'll give you two things. I'll give you a link to the software, the simulation software, and I'll also give you a picture of the cover of the lab manual. I mentioned this before, but be careful when you buy the lab manual because the lab manual, the textbook, and then they have something called an activities manual. They all look the same, but if you look closely on the lab, it'll say lab manual on it in small print. So I'll give you a picture of the one I have. I think I might have I want to say the fourth edition. I think the third will work just fine, but I'll put that in the next day or two. So you want to start thinking about getting that lab manual, and the lab manual, if it says with CD, it should come with the CD with the simulation software already in it. But just in case you get one that doesn't, since you're buying it used, I'll provide you with a link for the software that you can download. And you do want to try to get that at least a week before we get ready to start labs in case you have any software issues. So far as I know, everything should work fine on PC. I don't know if you got a Mac. I don't know about Mac. So that's the first thing. The second thing is this is week 3, right around probably around week 5. I like to do the first exam. So we'll have exam 1. I'll say more about exam 1, but exam 1 will cover week 1, 2, 3, and 4. So nothing to freak out about right now, but just kind of get that on your radar, know that that's coming, and I'll have more to say about that later. So I want to start today, talking about today, is actually a pretty important lecture, so important that I'm going to do two things. I'm making this video because I wanted to live stream this information about number systems. I also sent you a PowerPoint, but I also made a PowerPoint to go along with the video. So what I recommend is that, especially if you're not looking at this live now, if you're looking at this later off YouTube or off the website, watch this video first, make sure you understand what's going on, and then watch the one on the PowerPoint. Watch that second, and then I think things will make more sense. So I made 2 videos. I know that's an extra hour for you guys to look at this stuff, but I think it'll do you some good. It's not particularly hard, but it's new, so it can get a little confusing if you're not clear on what's happening. So I think between what we're going to do today and the video I made over the PowerPoint, I think you guys should be in good shape. So let's kind of look at what we've done so far. We started the course. I gave you an introduction to PLCs. You know that a PLC is basically I call it a computer on steroids. It's a computer designed to work in the industrial environment, used for some kind of process control. So we talked about that. The other big concept we talked about was this idea of analog quantities and digital quantities. And that's important for us because most of the things we want to monitor, or most of the information we get from devices that will do the monitoring for us, are analog. Most quantities in nature, analog. But I want to use that analog information in a computer, in some kind of machine, and so that's digital. And so we spent time talking about the differences between analog and digital, and how you would go from an analog signal to a digital signal. And why would you want to do that? There's a certain advantage, or several advantages, that digital has over analog. So we went through that before during the first week. Now, when you digitize something, you basically end up with information that's stored as a number. So I want to go into that because of that fact. We're dealing with numbers. That was the first week. The second week, last week, we looked at different parts of the PLC. So if you had a chance to look at those videos, we talked about the CPU, we talked about I/O modules, and we just kind of gave you an overview of the hardware. Today, we want to go into the CPU and understand how machines think, how the machines record information, how's it displayed? So I want to get into number systems because as you'll see here in just a second, everything's a number when you get into a digital device. So we'll get started. So what we're going to do is we're going to look at these number systems, and we're going to look at several types of number systems. So we're going to look at a base 10 number system. That's the one that we as humans use. Base 2, actually that's the one that we use when we talk about numbers and machines. Machines use base 2. And there's a couple others. We'll look at base 8. That turns out to be important for what we do in this class. And then base 16, that turns out to be important. As a matter of fact, and hopefully you can see this in the camera. I didn't get a chance to check the picture because my other computer wouldn't load up. But you can see down here, this says base any. Actually, we have these standard bases, base 10, 2, 8, and 16. But you can have a number system with any base you want. Matter of fact, what we'll do is we'll make up a number system. On exam 1, I'll ask you to make up your own number system, or I'll give you a made-up number system and ask you to convert it to decimal. So you'll see once we go through this that even though we're talking about these specific number systems, you can make up your own number system if you want to do that. So we'll look at that in some detail. So we'll look at these number systems, and as I said before, the most important two that we'll look at out of the 4 that we'll look at is base 10 and base 2. Base 10 is important because we as humans, we deal with base 10. Base 2 is important because machines deal only with what we call machine language, but that's based on base 2. So these are the most important ones. The other two are kind of there for convenience, and you'll see the application of those later on. So those are the ones we'll look at. Now, why do we want to study number systems? So why do we want to do that? Well, the reason is actually pretty simple, why we want to study number systems. If you think about it, you have some analog quantity out here. And this is a good marker. So you got some analog quantity out here, and you wanna monitor that. So this could be temperature, this could be a speed, a pressure, whatever. You got some kind of analog quantity, and you want to get it over into this machine. This machine called a PLC or whatever, some kind of digital machine. So the way to do that is you got to first go through a process of converting the analog to digital. So it's this device called an ADC, analog to digital converter, that we have to send this analog information into, and then what comes out is the digital information. Now remember, digital itself is basically just either numbers or codes. So what I might get here out of the ADC, analog to digital converter, I might get some kind of number or code that might look something like that. And that's what we send into the machine to store the data or information. Doesn't matter what kind of information this is right here. It could be a video. It could be sound. It could be a color. It could be a picture. It doesn't matter what it is. No matter what it is, when I digitize it, it's going to be stored or converted to a number. And the type of number that it's converted to is called a binary number. And binary is what we mean by base 2. So that's why this is important, because base 2 is known as machine language. Machine language or binary. So here's the process we go through. So by understanding these different number systems, it actually helps us understand how these machines think a little bit better if we convert these numbers to binary and different bases. So this is the reason why we want to look at number systems. So let's start by giving you some general information on number systems. So you express a number system, number system like this. So what you have is you have what we call the base, and then you have the power. So we can express any number system, or we can name any number system like this. So this right here is called the base. It's also called the radix. And I like the word base. And so what this does, the base, it tells you the number of symbols used in the number system in question. So the base tells you the number of symbols in that particular number system, and this right here is used for what you probably call in school place value. You remember place value when you're in like second grade. Now the place value, when you talked about place value in like, I don't know, second grade or third grade, you talked about the place value of a number. What we're going to refer to that is, we'll call that the weight. The weight. So the weight and the place value are the same thing for us in here. So we can express any number system like this. The base tells us the number of symbols used in that number system. And the power is going to give us the weights for different position, or the place value. And there's one other thing, that I can take the base minus 1. So if I take the base minus 1, what that'll tell me is the value of the highest symbol in the number system. Now, I don't know if you can see this because I kind of got this stuff squished together, but hopefully you can see it. All right, so we express or name a number system like this: the base or radix and the power. The base tells you the number of symbols used in the number system, and the base minus 1 gives you the value of the highest symbol. So what I want to do is I want to compare two different number systems. I want to compare the one that we as humans use, which is base 10, and I want to compare that to the one that the computer will use, which is base 2. So let's look at both of these number systems. As I said before, those by far are the two most important. All right, so here is base 10, and over here I'll have base 2. So if I express it like this, b to the n, then what I will write is this: 10 to the n, like that. And this is my base. So remember, the base tells you the number of symbols used in that number system. So there's 10 symbols in this particular, in the base 10 number system, there's 10 symbols. If I take the base minus 1, 10 minus 1, I get 9. The base minus 1 tells you the value of the highest digit or symbol in the number system. There's 10 of them, and the highest symbol is going to be 9. And so if I list those out, you already know what they are. The symbols I'm allowed to use, I can use 0, I can use 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's all I can use in the base 10 number system. Well, if I'm counting, what if I run out of symbols? So what happens is, then I start to repeat. I go 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. And again, I've run out of digits again, so what do? I change this to a 2, and I start to repeat. All I'm doing is using these 10 digits right there over and over again. I just keep repeating and adding a number column. So that's a base 10 number system. 10 symbols, highest symbol is a 9. Now the other thing that you looked at in grade school or somewhere along the line was this idea of place value. Let's look at that, place value. So what you probably learned when you looked at this, you probably said something like, all right, if I got, let's say I got a 4-digit number, and the place value here would be, this is the ones place, this is the tens place, this is the hundreds place, and this is the 1000s place, and I can keep going if I wanted to. Over here, I can put a decimal point, and I can go to the left, be tenths with a TH, hundreds with a TH, and so forth. We won't deal with decimal numbers here. We'll keep it simple. So here's what you mean by place value. Now, when you write a number system like this, I said that that's the base. That tells you the number of symbols in the number system. But this gives you information about the place value. See, if you start counting, now remember, as humans, when we count, we start counting with 1. We go 1, 2, 3, 4. Machines start counting with 0. So from now on, we're going to think like a machine. We're going to start counting with 0. So we won't go not 1, 2, 3, 4. We'll go 0, 1, 2, 3. That's what we'll do. We'll start counting with 0. So what you can do is, if you start counting these positions, like right here, this is position, this is the 0th position, this would be the 1st position, this would be the 2nd position, and this will be the 3rd position, 4th, and so on. If I count like that starting with 0, then what you can do, you can take this position number and you can put it in there for the base and get the place value. So here's what I'm saying. I'm saying that what you can do, instead of writing the place value like this, then what you can do is you can say this right here is 10 to the, that's the 0th position. This is 10 to the 0. This would be 10 to the 1st. This would be 10 to the 2nd. And this would be 10 to the 3rd. So I got a 1, I got a 10, I got 100, I got 1,000, and so forth. Now, the beauty of doing it this way, instead of writing it out like this, is when you do it this way, you can get the place value or weight of any number system. I mean, I can generalize this like this. If I want to, I can say any old number system place value. This is going to be B to the 0. This will be B to the 1st, B to the 2nd, B to the 3rd for any old number system. And this is what's going to allow us or you to make up your own number system if you understand this. So we'll write it this way. And remember, what you call place value, the ones, the tens, the hundreds, the thousands, in computer science, we call that the weights. This has a weight of 1, this has a weight of 10, this has a weight of 100, 1,000, and so forth. Now, when we look at these weights, what exactly will the weight tell us? Well, here's what the weight will do for us. You got to give it a value. So let's give it a value. Let's say that the value, this value has a value of 1. This has a value of 0. This has a value of 2. This has a value of 4. So you got the number 1,024. And what exactly does that mean when I reference it to these weights here, to the place value? Well, what you mean when you do that, what you mean by that is you got one of these, you don't have any of these, you got 2 of these, and you got 4 of those. That's what you mean. You write it out like that. What you're saying is you got 1 times 1,000, and you have 0 times 100. You have 2 times 10, and you have 4 times 1. And if you do the math here, I get 1,000 here. I don't get anything there. I get 20 there. I get 4 there. If I add these up, I get the number back, 1,024. So this calculation is what you mean when you give a number a place. You have a weight and a value, break it out, and this is what you mean by that number. Well, it turns out that all number systems work exactly the same way. This one you know so well, you're familiar with it because that's all you've been taught. You've been taught base 10, we count in base 10, we do everything in base 10. But this will actually work for any number system. So now what I want to do is apply the same logic to base 2. How would that work with base 2? So this is called machine language. Base 2 is machine language. Well, for base 2, if I go back to my representation of number systems, I have b to the n. The b tells us, the base tells us the number of symbols. So if I have a base 2, I got 2 to the n. What that means is I can use, in this number system, there's 2 symbols. And if I take the base minus 1, it tells us the value of the highest symbol. So that's a 1. So I'm allowed to use 2 symbols, 0 and 1. 1 is the highest value. So if I was counting, just like when I counted from 0 up to 9, and once I got to 0 and I got to 9, I had to go 1, 0, 1, 1. I had to start repeating this column. You do exactly the same thing here. In binary, if you were counting, you only got 2 symbols, so you got 0, you got 1. If you want to keep going, you have to go 1, 0, and then 1, 1, and then you have to add a column just like you do in base 10. It's exactly the same. The only thing that's different is this is 2 to the n. Over there we had 10 to the n. But the rules, the logic is exactly the same. And so just like with base 10, we have place value. So over here what we had was this. We had a 4-digit number. And we said that this was the ones place, this was the tens place, this was the hundreds, and we said this was the thousands. But what we said was we're going to write it this way. It's better to write it this way. 10 to the 0, 10 to the first, 10 to the second, and 10 to the third, because then that power also gives you the position of the value right there. This is the 0 position. That's the first position. Remember that we start counting as a machine, we start counting with 0. I'm going to do exactly the same thing with base 2. So in base 2, what we have, the value, the place value here, like this is 10 to the 0. Well, this will be 2 to the 0. Like this is 10 to the first. This would be 2 to the first and 2 to the second. This would be 2 to the third. But if I write it out like this, then what you have, you can see, and right here I get a 1, right here I get a 2, right here I get a 4, right here I get an 8. You can see if I keep going to the left, you just double. With base 2, only base 2 with doubles. So I go from a 1, a 4, a 1, a 2, a 4, a 8, 16, 32, 64, 128, 256. I can keep going. So no matter what number I give you, you can see here it's pretty easy. As you go add more digits to the left, just double what you had before it. So what exactly does it mean if I do something like, now I'm only allowed in base 2 to use 0 and 1. There's no 3, 4, 5. There's only 0 and 1. So what I can do is, like here, I had 1,024. I'm allowed to use the symbol 0 through 9. So I can use a 1, a 0, 4, up to 9. Here I can only use a 1 and a 0. And I showed you what you meant. When you write out this, you mean that you have 1 of these. You don't have any of these. You got 2 of these. You got 4 of those. Add them up, you get 1024. I can do exactly the same thing in binary. What if I gave you this? A 1, a 1, a 0, and a 0. Or I'll put it down here, a 1, a 1, a 0, and a 0. Now, we got a problem. I'm going to pause. I want everybody to hear this. If you're watching this live or if you watch it on YouTube, hear what I'm saying right now. I want to show you something. The problem is we're going to work with at least 4 different number systems, and maybe some that we make up on our own. But we got at least 4 different number systems. So let's say you walk out of the room and I have this on the board, and you come back into the room and you see that. What is that? I mean, what is it? Is that the number 1,100? Or is that the binary number 1100? You have to say what you mean. So since we're dealing with different number system, from now on, you have to show me what system we're in. Either in the problem statement, it has to be stated, this is a binary number, this is a decimal number, this is a hex number, whatever number system we're in has to be clearly stated. Now, the way you do it typically, if that's a base 10 number, you put a little in there. So then that would be 1,100. If that's a binary number, then I have to put a little 2 there. So there's other subscripts we can use that I'll show you later on. Now I'm saying this because on quiz 1, I gave you a problem statement. I was very clear on the problem statement of what I was looking for and the type of switches that you can use. And some of you, instead of using, I think, a normally open push button or normally closed push button, you got that confused and you used relay contacts, which you use this, and you were supposed to use these symbols. And I told you, you got to use the right symbols. Now, I wasn't trying to be a behind, but in this class, you have to say what you mean. If you mean this, you show that. If you mean that, you show these are not the same. And if you get the logic right, but the symbol's wrong, the whole problem's wrong. And why am I saying that? Because I don't want you upset with me if you leave this little 2 off and you say, I should get partial credit for that. I just left the 2 off. There's a hell of a difference between 1,100 in decimal and a 1100 in binary. If you leave that 2 off and it should be a 2, it's wrong. You got to tell me what it is. So I don't want to get these emails saying you're upset or you don't think it's reasonable, because I'm not giving partial credit if you don't get that right. That's important. If you're running some kind of process, that can mean the difference between life or death if the process you're running is mission critical. So that's very, very important that you subscript and you say what you mean in this class. The other thing I get is in lab. The lab is coming up in a couple of weeks. You can give me a perfect program that works. Everything is right in the program except for you give me this symbol and you should have gave me that. If you do that, then the problem is wrong. If you mean a normally open situation, you gotta show me that. If you mean a normally closed, there is no partial credit for that. So you got to learn these symbols well, and if it's something I'm not clear on, then it's your responsibility to ask me to make sure we're clear before you do a lab or a quiz or something like that. People will lose points on the labs, and the quizzes are not that bad, but the labs are 20%, and that can have a big sway in your grade. So make sure you get these subscripts right. I'll remind you of this as we go along. But on quizzes and exams, that's your chance to show me that you've mastered what I've shown you on these videos or on the PowerPoint. So make sure you get these numbers right. So back to this. So what I have is a 1100, and just like over here, when I had a 1024, this means I have one of these. I have 1,000. I don't have any hundreds. I got 2 10s and I got 4 1s. This means exactly the same thing. What this means in binary, is I have one of these, so I have 1 times 8. I got one of these, so I have 1 times 4. I don't have any of these, so I got 0 times 2. And I don't have any of these, so I got 0 times 1. So here I get an 8, here I get a 4, here I get a 0, and here I get a 0. If I add it up, I get 12. I get a 12. Now, what's the meaning of that? What that means is that if I have a 1100 base 2, in our number systems as humans, what that is for us, and what that converts to, is a 12. Now that 12, I don't know what base that is. If I write it like that, that could be base 8. That could be base 18 or base 18. That could be base 16. If it's a 12, I got to subscript that with a 10. So when you enter into your machine, the number 12, what actually goes into the machine is this, a 1100. So you can use this to go from, this is actually called, the way we usually show it is like this. We just put it in boxes. And you'll remember this. If you write it down this way, you'll remember it. So what you do is you go 8421, 8421, and put it in boxes like this. So that's called 8421 code. And if you do it that way, you can quickly decode any binary number I give you. Like if I give you the number 1001, that means I got an 8 and I got a 1. That's a 9 base 10. So a 1001 base 2, that's to a computer, in our world is a 9 base 10. You type in a 9 on the keyboard of your cell phone, what gets stored in that cell phone for that digit 9 is a 1001. So here's human language. We call this machine language. Now, this is a good place for me to, I've been using two terms. I want to make sure you're clear on these two terms. What's the difference between a number and a code? That's important. So this is for binary. I'm talking binary. So I have a binary number. I'm going to have a binary number. And I can have a binary code. What's the difference between the two? And the difference is this. A binary number will always have place value. So I would use this right here. So if I give you, I don't know, if I give you 1101, you can do this right here. You can say, all right, that's 8421. As I said before, if I go that way, I just keep doubling it. If I want to add another one, it'll be 16, 32, and so forth. But that means I got an 8 and a 4, that's 12, and a 1. That's 13, so 1101 base 2 in our number system is 13. So you can do it like that when you convert it over. But if that's a binary number, then it has place value. All binary numbers have place value. Binary codes can have place value, but they don't have to have place value. So let's say I have a piece of analog information. I want to digitize it. So I can use a number like this to digitize it. So let's say I got this picture. I got a person, I got a house, and what I want to do is I digitize this, so I break it up into points. So when I'm dealing with videos and pictures, we call it pixels. So maybe this pixel right here, this piece of the house, that pixel right there, I'm going to use this number to represent 1101 base 2. When I'm saying I'm representing that pixel right, that's a big pixel, by the way. A pixel is like a dot. But I'm using that pixel right there. I'm going to represent that as a 1101, or I'm going to use a 13 in our number system to represent that pixel. But if I represent it as a binary code, I don't necessarily have place value. Maybe this pixel right here is represented by just a sequence of bits. Maybe that piece is a 1101, and maybe this piece is a 1010. So I can use a code. It could have place values. We will deal with several codes in the class that actually have place value, so they'll be similar to a binary number, but they don't have to have place value. It's just a sequence of numbers. When you code something or decode something, it's just a sequence of binary digits that makes one code different from the next. So the difference between a binary and a number code, binary numbers always have place value. Binary codes is the sequence of bits that will distinguish one piece of information from another piece of information. And sometimes these can also have place value, but when they do, it'll be clear because we'll name it. Like for one type of code we'll talk about is BCD. That stands for binary coded decimal. So it's a code, but it actually has a place value, as you'll see when we get to that. So understand the difference between a binary number and a binary code. So what you guys need to do, and I guess you need to do some practice with this. It's pretty simple. Once you see the 8421 code, it's pretty simple to do. It's not a big thing. But you should practice, if I give you a number, like if I say, if I give you a 1111, I say base 2, what is that in decimal? That could be a question on the quiz. What is that in decimal? So then you just do your 8, 4, 2, 1. I got an 8, I got a 4, it's a 12, 14. I can add it, I'll get a 15. I can add it all the way up and get a 15. You should be able to do something like that pretty quick. So I don't really think I got to give you practice because this is so simple. But if you want some practice, just send me a text and I'll make up some problems and put them up for you. But I think that's pretty simple to do.
Okay. So, question.
Yeah, go ahead.
For the binary code, I know when you add up the weights, you add a base 10 to the bottom. But why is it specifically base 10? And would that change if you had a different, like you said, you had a different base, say base 10?
It would change, yeah. So, yeah, it would change. So let's say you have I think I heard 2 questions. So if I have a binary code, it could have place value. So like, let me show you this right here. So this, if I have a 1100, we've already done that one, right? So you know that means I have an 8, I got a 4. So this right here in our number system, that's a 12, right? Well, there's a code called, one of the codes we'll look at several. One is called BCD code. So it looks just like that. That could be BCD code. The way you would express that is like this. You just subscript BCD. So now I now know it's not a weighted binary number, it's a code. So with any code, there'll be a way for you to subscript it. Now, the other question you asked is actually a pretty good one. So let's just delve into that a little bit. So here's another, I can just kind of jump ahead here. Another number system we're going to deal with is base 8. Now, why are we looking at base 8? Machines don't understand base 8. We as people don't understand base 8. So why are we looking at base 8? Well, one of the reasons to look at base 8 is because 8 bits make up a byte. And so that number 8 kind of fits naturally with this base 8 number system. And so where this comes up is usually there's something called addressing we'll talk about. You know a little bit about addressing already. You have a screw terminal that you're going to connect a physical wire to that connects to a switch or sensor. In some kind of way, the position of that screw terminal and what it's connected to has to be recorded in the CPU of the PLC. And so some kind of way there's a mapping. Well, we do that through addressing. And I talked a little bit about that. I know in the other video I talked about addressing. We'll get more into it. So often when you deal with addresses, they'll express addresses in base 8 or base 16. So that's the reason why we'll look at that. But we can actually just jump ahead and look at this because this will answer your question. So if I have, it's clear what base 10 looks like. So base 10 was like this. This was 10 to the 0. This was 10 to the first. This is 10 to the second. This is 10 to the third. So this had a weight of 1. This had a weight of 10. This had a weight of 100. This had a weight of 1,000. So when I did 1,024, you know what that means. You know to take this times 1,000. I don't have any hundreds. I got 2 10s and 4 1s. And we did the same thing with binary. It works exactly the same way with any base. So if I want to do a base 8, what I would do, I'll just do 3 of them. This would be, you might have to help me with my math here. This would be, just like this is 10 to the 0, this would be 8 to the 0. and this would be 8 to the first, and this would be 8 to the second. So a base 8 number system would look like this. The weight of this first one would be a 1. The weight of this would be an 8. The weight of this would be a 64. That would be the weight. So that's different than over here, right? We had a weight of a 1, 10, 100. It depends on the number system as to the weights, but this is for a base 8 number system. Now in this 8 number system, remember I have 8 to the end. The base tells you the number of symbols. So there's 8 symbols I can use. And then if I take the base minus 1, it tells you the value of the highest symbol, 7. So in base 8, if I were counting, I go 0, 1, 2, 3, 4, 5, 6, 7. I'm not allowed to use an 8. The symbol 8 doesn't exist in the base 8 number system. And so what I would do is I start repeating. I go 1, 0, 1, 1, 1, 2, all the way up to 1, 7. And then I got to change this to a 2. And I got to keep flipping that first digit. You might remember that table I showed you. If you watched the video, I showed you a diagram of the input image table and the output image table. If you go back and look at that diagram, and what I mentioned was you have, if you know what I'm talking about, you had a row. It was an output image table. You had an output image table. It started with an O. It was an input image table. The row started with an I. And then there was these bit numbers. It went from something like this was a 7, this was a 6, it might have went the other way. I might have had a 0, 1, 2, 3, 4, 5, 6, 7. And then there was a space, and then it started over here. It started with a different number. It started like with a 1, and then it started counting over. I said, look at that weird number system. Well, this was an octal number system. And so in octal, you can't go with there's no 8. So that was, if you go back and look at that, you'll see clearly what I'm talking about. But let's say I gave you, here's the weights to a base 8 number system. Let's say I gave you, I'll make it easy. I'll make this 0, I'll make this 2, and I'll make this 3. Now what I got to show is you can't just write a 0, 2, 3. Okay, it's clear here because I wrote the problem, so I know this is base 8. But if you were showing this to me and you didn't want to lose credit, you really need to stick a little 8 right there so I know that this is base 8. And then what this is going to convert to, this is going to say, all right, I got 0 times 64, so I don't have any of those. I got 2 times 8, and I got 3 times 1. So I get a 0, I get a 16, I get a 3, that's what, 19. So what you would say is, what is it? 0, 2, 3, base 8, and our number system is a 1, 9, base 10. So basically, once you learn one number system, you can do any number system because they're all done the same way. The only thing you got to get right is you got to get these weights right. But if you remember, if you generalize it, just remember that whatever base it is this base to the 0, this base to the first, that same base to the second, and that'll give you the weights. And then you just got to remember which symbol to use. The highest symbol you can use will always be B minus 1. So here, base 8 minus 1 was a 7. So in this place, I can use a 1, 0, 1 through up to 7. I'm not allowed to write an 8 there because 8 doesn't exist. And so we'll do this same thing. Well, I'll go back through this again because I kind of jumped ahead. This is actually the next video. But we'll do base 8 and we'll do base 16 because those are the ones that we use a lot in this class and just in computer science in general. So that's a good question. Now, on the exam, what I'm going to ask you to do, on the exam, I'm going to say, okay, make up your own number system. What if I tell you to make up a base 5 number system? How would you do it? Well, simple. Base 5. Base 5 means I write it like this. The base tells me the number of symbols, and 5 minus 1 gives me the highest symbol in that number system. So I can use the digits 0 through 4. And then what you do on the exam is you put some spaces out like this, And you say that this is 5 to the 0, this is 5 to the 1, this is 5 to the second, this is 5 to the third. You say, all right, well, that's a 1, that's a 5, that's a 10. No, that's not a 10. 5 to the 0, first, second, that's a 25. What's 5 to the third? 5 times, I don't know what that is, but you see what I'm saying. So I can have I can use any. What is it? 125.
Yes, sir.
125.
Mm-hmm.
Thank you. So what if I can use, now I'm not allowed to put a 5 there. If you do that, it's wrong. But you can use the symbol 0, 1, 2, 3, 4. And probably what I'll do, I might have you make up your own number system, or I might say, hey, you got a base 5 number system, and here's the number right here that you have. That's base 5. Now convert that to decimal. And all you would do is multiply this times that, multiply this times that, multiply this times the weight, add it up, and you got the value in base 10. So any number system, this will work for. That is a very good question.
This is a more hypothetical question. When you have like the weight base 10, would the whatever device you're working with interpret what the actual digits are and whatever number system you're using based on what it knows, basically? Like, say if you had a device that was using base 8 number system and it had X amount of slots available, it would generate the weight base 10 in terms of
no. If you use, no matter, that's okay. Don't confuse these number systems with what goes into the machine. It's impossible to put a base. Let me look at I'm looking at the computer. I gotta look at you. That's bad. So here's the machine. And I don't care what you do. If normally what you're gonna do is you're gonna put in a base 10. That's the most common. When you dial something on your cell phone, you hit the digit 1. That's base 10. When you enter something in your calculator, it's exactly what we're doing here. That's all base 10. So normally I would say 95 times out of 100, you're dealing with base 10. But you cannot enter a base 10 number directly into the machine. There's always going to be some kind of conversion. It's going to convert that base 10 to binary. The only thing you can send into this machine is binary. What's the same with this is base 10. I don't care if you had base 8, so you can have base 8, we'll deal with base 16. You can make up your own base. When you send it to this machine, it's got to be first converted to binary. You can't send a base 10 or base 16. You can't send any other number into a machine other than zeros and ones. So if you have, there are people that actually program. You might have heard of machine language. There's people that can actually write a whole program in machine language, and what that means is they can program just using zeros and ones. Now, there's not a whole lot of people on the planet that can do that, and that's all they can do in life. They can't tie their shoe, they can't pick their nose. All they can do is zeros and ones. But for the rest of us who are not that smart, we got other ways of putting information into a computer. So when you type the word print on the computer, or when you drag and drop an app on your cell phone, even though you're dragging and dropping, you're actually giving the cell phone the command, and that command has to be first converted to binary. So no matter what gets into here, it's converted to zeros and ones. So I don't care what the number system is. If you're dealing with base 8 and you're going into a machine, you got to have some kind of algorithm or some kind of device that will convert the input number that's not base 2 into a base 2 number. Does that make sense?
That does. Thank you.
That's a good question. You guys are, how many people do I have out here? 24 out of 36. That's not bad. You guys are asking some good questions. I wish I could see your pictures. But when you show me your pictures, so I can get to know you. I know some of you from the circus class, but when I turn the pictures on, and it crashes the application, so we can't do it. But you asked some really good questions. I only have 8 minutes, so let me go through the other part. It's actually pretty simple. we have a problem. Now, before I get into this, please make sure you watch the PowerPoint video. I'll put it up, this video and the other one sometime tonight, because there's portions of that PowerPoint that I'm not going over. I'm just skipping over it. I want you to go through to get the full thing. But I think that watching this first and then looking at the PowerPoint, it's going to be crystal clear when you look at the PowerPoint because you're doing this first. But one problem we have is the problem of negative numbers. How do I handle negative numbers with digital devices? Suppose I had a temperature, analog temperature, and it was minus 32 degrees. That's a practical problem right there. How do I handle negative numbers when, see, if I have a, say I can have a +5 or I can have a -5. And base 10 is simple. If you mean positive, you write the positive sign in front of it, or you don't write anything at all. If you mean -5, you just put the little negative sign in front of it. It's understood. I know what you mean. But the problem is when I convert that to binary, you can't put a plus. You can't put a +1. The plus sign doesn't exist in binary because in a computer, everything is represented as a 0 or 1. You can't. The plus sign wouldn't make sense. So how do I represent negative numbers in machines? How do I do that? Well, it turns out there's three main ways that we can do this. So write this down. This is in the PowerPoint too. I have it listed out. But the first is to use something called a sign bit. So I want to go out, talk about that. Second is something called I'll put it like this, the ones complement. And then the third way is the twos complement. Oh, I forgot. There's one other thing I want to do too. I want to show you how you can convert a number. I showed you how to use the 8421 code to convert a number from a decimal number to binary. There's another way called the divide by 2 method. So at the very end, I'll probably run out of time, but just give me a couple minutes. I want to show you that because I actually have that in the PowerPoint. I want you to understand what I'm doing. So let's look at this as I've already started, and then we'll go back to that divide by 2 method, and then that'll be it for the video. So with the sign bit, what I do is, well, here's a way to think about numbers. So in a computer, I have this numbers. Now you know what a bit is. A bit is a 0 or a 1. You know what a byte is. A byte means I got 8 bits. So those are standard. But there's this thing called a word. Words are not standard. A word is a group of bits, and the word size depends on the machine. Whoever designed the machine, they can make the word size whatever. It's just got to be some power of 2. So I can have a word that's 8 bits about the same as a byte. Now for us, in the class, we're going to use 16 bits is one word. And that's just for our purposes of our class. So what we have, this is a word. This is one word for us. And I'm saying it's 16 bits. Actually, let me do it like this. It's 16 bits wide. So it's 16 bits from there to there. And so this would be bit number 0. This will be bit 1. I keep going, and this last one is bit number 15. Well, right here, when I get to bit number 7, then what you have is you got this part right here. That's called my lower byte. And you got this part right here. This is my upper byte. can name parts of a word. You have the lower 8 is my lower byte, and the other 8 to the left, that's my upper byte. And then the other thing you can do is the leftmost bit, this right here, the leftmost one is called my MSB. That stands for most significant bit. Most significant bit. And this right here, that's my LSB. That's my least significant bit. I think in the video I show you that if you have money, say you have $1,024, well, this would be your most significant number, and this would be your least significant number, right? I mean, this is $1,000 and this is $4. Which one would you rather lose? If you had to lose one, you probably want to lose $4 and not $1,000. So it works the same way here. This leftmost bit is my most significant bit, and this rightmost bit is my least significant bit. So that turns out to be important in just a second. I'll come back to that. But let me give you, let's go back to this sign bit thing. So one way to represent a negative number is to use a sign bit. So let's say I have the number 5. I have a +5 and I have a -5. And this is base 10. And I want to show that in binary. What I could do is 5 will be a 1, 0, 1 base 2, right? I got a 4 and a 1. I add that up and I get a 5. So in binary, 5 will be 1, 0, 1. So I got 1, 0, 1 base 2. Now to show us a +5, what I can do is I can say, all right, any leading number, the leftmost bit, if the leftmost bit is a 0, then the number is positive. If the leftmost bit is a 1, then the number is negative. So that's one way I can do this. So what I can do is I can say right here, I can put a 0 here, represent a +5, and I can put a 1 there to represent a -5. But if I do that, then you got to remember the least significant bit or the most significant bit and the least significant bit. Now, if you just walked into a room and you saw a 1, 1, 0, 1 base 2, you don't know what it is. I have to specifically say we're using the sign bit. If I tell you we're using the sign bit, then now what you know is only this part of the number is the magnitude. This right here is the, so this is not my most significant bit. This right here becomes my most significant bit, and this is the sign bit. And so right here, that would be a 5, and since I have a 0 there, it would be a +5. And the same here, this would be the magnitude of the number, which is a 5, and since I have a 1 there, so the 1 is negative, this would be a -5. So if I do that, I got to tell you, hey, we're using a sign bit here, and you know how to apply this. So one way is to use the sign bit to show a negative number, but there's 2 other ways. Now I'm out of time now, so if you guys got to check out, you can sign off and I'll just look at the video when I record it. I finished this, and I want to show you how to do that divide by 2 method. I probably need another 5 or 6 minutes and then we're good. Okay, so one way is to use a sign bit. Sign bits are used, but they're not used that often. Most of the time we're going to use these other 2 methods, and they're pretty simple. So let me show you how they work. The ones complement is really, really, really simple. All you do is flip the bits. So if I give you a binary number, say I gave you the binary number 1101, and I say, all right, take the 2's complement of that. So this is a binary number 1101. The ones complement. I said the 2. The ones complement. All you would do is flip the bit. So where there's a 1, you write a 0. 0, where there's a 0, you write 1, 0. So this right here is the ones complement of that number. The ones complement, all you do is flip the bits. Now don't worry about what we're going to do with this. That comes later. I'll show you how using a negative number. Really, this is is the one we want to get to. That's a little bit more powerful, but you'll see the application of this later on. Just understand how to do it, because on the quiz, I might ask you to give me. And by the way, the quiz is coming up this Friday. Well, it won't be over this material. It's over last week's material. So I'll send out an announcement. I want to make sure you study the right stuff. So the ones complement, all you do is flip the bits. If it's a 1, you change it to a 0. If it's a 0, you change it to a 1. So here's the ones complement of that number. The twos complement is a little bit more involved, but it's still pretty easy. So let's say I give you this binary number. I give you a 1, 1, 0, 1, 0, 0, like that. I give you that binary number. This time I want the twos complement. Now, if you look at it online, they're going to tell you to do it a different way. If you want to do it their way, that's fine. I'm going to show you the way I like to do it because I think it's quicker, it's easier, and you won't make a mistake. So all you got to do is to get the twos complement is you start with the rightmost symbol or number, and you move to the left up to and including the first one, you leave them alone. So up to and including the first one, I just leave it alone, write it as it is. I don't change anything. But everything after the first one, you flip the bits. So up to and including the first ones, I'll leave it alone. Then I flip it. I take the ones complement here. That will go to a 1. That will go to a 0. And that will go to a 0. So here's the twos complement of that number. So up to and including the first one, leave it alone. Anything after that, take the ones complement of it, which means just flip the bits. Now, you'll see in the PowerPoint, I give an example of this, and you'll see how to do it. But if for some reason it's not clear, you can ask me, and we can hook up this camera thing, and we can do some more of this on the board. So, sign bit, I don't really use that a whole lot, but understand what it is. 0 for a positive number, a leading 1 for a negative number, and then the second to the left digit becomes your most significant bit. The ones complement, you just flip the bits. The twos complement, you keep the numbers the same. Start on the right, keep the numbers the same up to and including the first one, and then everything after that, you flip the bits, and you got the twos complement. Now, if you look online, they're going to say, I think they'll say, to do the twos complements, take the ones complement and then add 1 to it. And you'll see it has the same effect of doing this. But I think this way I'm showing you is quicker. So hopefully that's clear. If not, you can ask questions. Now, the only other thing I'll do, let's just take a couple minutes. In the PowerPoint, I show you how to convert a decimal number to binary using what we call the divide by 2 method. So I'm going to go over that example, and then that'll be the end of the video. We'll be done for today. So let me show you how that works. So all you do, so I think on the PowerPoint, I think I use a number 47. I believe it's a 47. So I got 47 base 10, and I want to convert that to binary. So one way to do it would be to, do my 1, 2, 4, 8, 16, 32, 64. I can box this up, and I can figure out what fits where. That's one way to do it. But the divide by 2 method, if you have a bigger number and you don't want to write all this out, actually works pretty well too. So all you do is this. You divide by 2, and then the remainder becomes, if there's a remainder, you'll either have a remainder of 1 or 0. The remainder becomes the bit that you're looking for. Now, it's harder for me to say. It's easier for me to show. So I want to convert this to binary. So what I'm going to do is keep dividing by 2. But there's one important step. There's actually 2 important steps I'm going to pause on that I want you to make sure you get. So we're going to divide by 2. So I'm going to say, all right, I got 47. I'm going to divide that by 2. So I'm going to divide by 2. That would be 23. And 23 times 2 gives me 46. When I do the subtraction, I get a 1. So I got a remainder of 1. So that's that 1 becomes a digit, one of the digits in the number I'm converting to. The thing is, here's the important point number 1. That's my LSB. It's not my MSB. That's my LSB. So know that the first number you get is actually your least significant. That's my LSB. And once you understand that, then you just keep doing this over and over again. So now I'm going to divide this number by 2. So I'm going to say 23 divided by 2. That is 11. That gives me 22. That gives me a 1. So my next number is a 1. And then I'm going to take this number and divide by 2. I'm just going to keep dividing by 2. So when I divide that by 2, that's a 5. That gives me a 10. I got a remainder of 1, so my next number is a 1. So far what I got is I got a 1, I got a 1, I got a 1. But remember, this is my least significant bit, right? So we got to keep going. I got to do that one now. So now I got to take 5. I take 5, take this one, divide that by 2. That's going to be a 2. That gives me a 4. That's a 1. So I got a 1. And then I got to take the 2. Where's my green? I got to take this. I'm going to go 2 divided. Let me erase that. I got to take the 2, divide by 2. 2 goes into 2 one time. 1 times 2 is a 2. So now I got a 0. So my next one is a 0. So that's a 0. And then I got to do it one more time. So watch how I do this. This can be kind of tricky, but watch how I do it. Just listen to how I say this. So now I got to take this, the 1. I'm going to go 1 divided by 2. 2 and the 1 doesn't go. So I put a 0 there. 0 times 2 is a 0. And then 1 take away 0 is a 1. So that 1 there, that 1 becomes my most significant bit. So I got a 1 here. But this right here is my most significant bit. So I really, probably what I want is write this the other way. So the actual number is I got a 101,111 base 2. Okay, so this is my least significant bit. That's my most significant bit. Let's call it the divide by 2 method. So I don't know, look at that, practice it up. I don't know. Doing the exams remotely is kind of hard for me because you guys have all the information right there. But if I ask you to do this, you should be able to do something like that. It's pretty simple. So practice it. If you have any issues or problems, let me know. The only other thing is I'll be putting up another homework. I think it's homework 3 or 4. It'll be coming up either today or tomorrow. That deals with binary arithmetic, which is going to be the next topic that we're going to talk about. Now, I'm done. Do you guys have any questions for me before we sign off? Any questions or comments about any material that we've covered today or anything in the past that we need to review? Any questions? Okay, well, if you have questions, send me a text, send me an email. You guys have a great rest of the day, and I'll see you guys on Friday.
Thank you.
Thank you.